Okay, thanks for tuning in and doing your pre-lesson study. So by doing this, basically you are helping yourself because your teacher will then have more lesson time to go through the more difficult subtopics in this chapter. So to begin, I have two good news for you. The first good news is there will be no more calculation for the next 3 chapters. And the second good news is that this particular chapter is very similar to the electrostatic chapter. So if you are very familiar with the way to answer the structure question, what are the components, how to draw your electrostatic field, you will most likely do very well in this chapter. Okay, so what this video will do is that I'm going to go through with you some main concepts in this chapter. For example, we are going to talk about how magnetism arises, and to do that, I have to introduce a new concept to you, and it is called domains. And by the way, there will be no notes, so you need to take down your notes, and I think your teacher is going to check your notes to confirm that you have watched this video and that you have picked out the key concepts that we'll be talking about later. Okay, then after that I have to introduce you to a new rule that has something to do with your hands. So for the next chapter, you'll be hearing things like right hand grip rule, and you have to use your right hand to do that rule, and you have your Fleming's left hand rule, and you will have your Fleming's right hand rule. So for those in Chinese called 左右不分, or you cannot determine which is your right and the left hand, it is time for you to find a way to differentiate right and left. Okay, so without further ado, let's begin our chapter, and I will minimize this thing and maximize my very cute magneto baby. Okay, magnetism. So before I go on and discuss about magnetism, do you know who invented the magnet? Any idea? Actually, it's a trick question. No one invented the magnet. Actually, the magnet was found. So legend has it that the Greek is the one that has discovered the magnet, and that the story goes that there's this farmer who was walking along the road one day, and his shoe nail, I do not know what is a shoe nail, but you can Google it, so I assume that it must be a metal part of his shoe, gets stuck onto one of the stones. So apparently this stone has some magnetic material embedded in it, and because of that, the magnet get attracted to the iron nail on the shoe, and so they discover this mineral that would be attracted to iron or steel, and they decided to name this material magnet. And legend also said that it is the Viking who because they have discovered the magnet and use it as a guiding compass that enable them to navigate to England and invaded England. But if we rely on historical record, it is actually the Chinese who first make use of the magnet as a tool to navigate. So fun fact, do you know how a magnet, how a compass work? Yeah, sorry, I always divert when I'm teaching. So anyway, this is a fun fact. So what happened is, I need you to look at the slide. Basically, a compass is actually a magnet. So and of course, I expect you to know that the rule of magnetism, similar to the rule of electrostatic. The rule of electrostatic is what? It says light pole attract, light pole repel, and light pole attract, right? So similarly, the rule of magnetism is that light pole will repel and unlike pole will attract. So what happens is that your compass is actually a magnet. So your compass will interact with the Earth's magnetic field, and it will only point at a fixed direction. So what I'm drawn here is actually a compass. This circle is the housing of the compass, and the needle of the compass is actually a magnet. So we decided that to name this your geographic north. That means whenever this compass needle is pointing, it is the north, and whenever the other end is pointing is our south. So we decided to name it like this. But if you think about it, so this bigger circle that I'm drawing is the Earth, the planet Earth. So if you are saying that this compass is pointing at north, and you know that unlike pole attract, so if this is north, then what is the magnetic pole on top of the Earth? If this is north, then what is it attracted to? The magnetic south, right? So actually our Earth, our geographic north is actually our magnetic south. So even though we call the top half of our Earth the north part, or we call it the North Pole, because this is how we define it geographically, but in terms of magnetism, it is actually the magnetic south. So actually the bottom of the Earth, which is our geographic south, is actually our magnetic north. Okay, so this is a bit of fun fact. So just now I've mentioned that magnet is actually found, and it is not being invented. That means not someone try to make it. Okay, it was found, and then it was actually found deep under the Earth. So what happened is that to explain magnetism, we have to talk about this thing called domain. So I'm going to skip this. Okay, in this science model, right, we are imagining that when we have a piece of material, instead of using the kinetic model of matter, we only learn two models. The first model that you learn is kinetic model of matter, and we learn that using that model, a solid is made up of particles that are in fixed position, vibrating about their fixed position, and there's very little gap in between them, and so on and so forth. But for this model that we are going to use, we imagine that this rod is actually made up of domains, and these domains is actually how do I know that? Why is it that I call this a domain? Because we imagine that all these particles are being grouped together as a domain. And why do we group them together? It's because that these particles are all pointing at a certain random direction for a non-magnetic material. So basically you can imagine that this domain are tiny magnets. And when I draw an arrow like this, it actually represents North Pole here and South Pole here. So actually all all materials are having this domain. But why is it that they are not magnetic? It's because these domains are not aligned. They are all randomly scattered. So let's say I have a north here, it is being neutralized by this north, and then this south is neutralizing this south. So because of the randomness of this domain, the direction of the domain pointing at random direction, there is no net direction, unlike this diagram that I'm showing you. So can you look at this diagram, and you can see that the domains are all pointing at a single direction, meaning that the north here will actually be aligning this domain, and then you can see that all your north is now pointing the right. So what happens is that when you zoom out and you view this material as a whole, then you will have a net North Pole on the right, and you have a net South Pole on the left. So in physics, I summarize, we imagine that a material is made up of domain. So for a material that has not been magnetized, its domain are all pointing at different direction. And because they are all pointing at different direction, there is no net direction. The domains are not aligned. So because of that, there is no net magnetic effect, and because of that, the material is not magnetic. But if we somehow manage to align this domain in one single direction, then this material would become magnetic. Okay, so you may ask me, teacher, so far you have told me that, okay, materials, natural materials, will have its domain pointing at all the different direction, and because of that, natural material is not showing any magnetic property. Then why is it that you say that in ancient time, magnet is being discovered? How can they discover something that is not naturally occurring? Remember the story that I told you about how the Greek farmer discovered that this stone will get stuck to his iron shoe nail. So what happened is that when let's say now this is half of the earth. So what happened is that when you have iron or some material deep under the earth, these material are actually under great pressure because of the thick layer of soil above it, and also because it is very near to the core of the earth. So the core of the earth is very hot. So basically when you have minerals deep under the earth, it is actually under high pressure and high temperature. So when you have high pressure and high temperature, that means the particles in this material, these minerals, are actually very energetic. It has a lot of energy. And because the earth has its own natural magnetic field, so the earth has its own magnetic field, right? I'm sure you have seen some NASA diagram that shows something like that, and then this is the earth magnetic field that is like 3D and it's like a butterfly, things like that. So what happens is that when you have a mineral that is deep under the earth and it is under high pressure and high temperature, its particles are very energized, meaning that they are very mobile. And because of that, and that you have a magnetic field from the earth, the magnetic field from the earth will start to slowly align the domains in a singular direction. So let's say this is the earth, and I have a magnetic field that goes this way. This way. So what happened to this mineral is that because its particles are very highly energized, okay, let's say at the beginning, the domain of this material is all haywire, all pointing at different direction. Okay, but because of this magnetic field, so there's a magnetic field from the earth, which is naturally occurring, going by this way, because the domain are very energized, so they can move around slowly, okay, although it's not like immediately change direction, but because it is very deep under the earth, so it has a lot of time, it has temperature, and it has an external magnetic field. So this external magnetic field is like a person, it's like a teacher shouting at a group of Set 1 students. So the Set 1 students, before the teacher come, they are all looking at different direction, right? So these Set 1 students are like your domain in a normal mineral. They are all looking at different direction. But once you have an external magnetic field who come here and you start shouting, hey! So what will happen? Your student will start to slowly but surely, although some of them, like you guys, will not listen, but they will surely eventually turn and then face the teacher, right? And then you will have a group of students now facing in a singular direction. So similarly, this external magnetic field will have this effect of slowly turning all these dipole and then aligning them in one single direction. And when this happens, when this condition is being fulfilled, then you will have a magnet that has north here and south here. So that is how magnet form, and you need to understand the scientific model that we use to explain how magnetism arises. Basically, it is the alignment of domain in a single direction. So magnetic domain, if you have an alignment of this domain, you can give rise to magnetism. And how would this domain align themselves? Well, you have to supply heat, you have to supply pressure, and most importantly, you have to have what? A teacher, right? You have to have this guy, an external source. You also need to have, let me get this, wow, very hard. You also need to have a external magnetic field. Okay, so how magnetism arises, how would you explain it? Well, I have to align the domains. How do you align the domains? Supply heat, supply pressure, and then align them with an external magnetic field. Then you need to know, as a pure science student, why do you need heat and pressure? Well, that is to give energy to the domain to align themselves. Without this energy, can they move? No, they can't move. And what is the use of the external magnetic field? Oh well, the external magnetic field will align the domain to a singular direction. What if there is no external magnetic field? Well, then although the domain has energy to realign themselves, they do not know align to where. Understand? So that is what the gist of magnetic domain.